Hey, this is T-Band, Flat Earth Part 2. Now, there are a few experiments that you can do to test the curvature of the Earth, and one is to find a length of land that is at least 3 miles long. The farther you go with this experiment, the better your results will be. But this experiment is based on the idea that the curvature of the Earth is such that a the Earth will is supposed to drop away from you uh, at about 8 inches per mile for the first mile, and then the mile distance squared times 8 inches for each succeeding mile. And so there's a formula for that. And when you're dealing with a distance between 2 points on the surface of the Earth that are at the same altitude, so they're at the same distance from the center of the Earth, the air pressure will be the same at the same altitude if you ignore wind blowing and stuff like that. But if there's no wind blowing, and so no pressure differences in regions, then air air density will be greater the lower your altitude and less the higher your altitude. So the nature of this experiment is that you find 2 points that are separated by a distance of at least 3 miles, preferably longer, like 5 or 10 miles. But the altitude, the curvature of the Earth, and the altitude should follow a curved pattern, and between any 2 points that are at the same altitude, there will be an intervening hump of the curvature. And if you had a perfectly smooth ball of the Earth, like with no mountains or valleys, and it was just a extremely smooth surface, like a billiard ball, or very, very flat like that, between any 2 points there would be an intervening hump of Earth. And if you were to draw a line between 2 points on a circle, that creates a chord across there, and there's a section above the chord, and that's the intervening hump, and it will block the view between those 2 points. So for this experiment, if you had a very sensitive altimeter, an altimeter measures pressure in a region and knows what the altitude will be, what the pressure is for each altitude at that point, at that location, at that position. And if you had a very sensitive altimeter, you could measure the altitude of, for example, a post that is put into the ground at one location, and then travel a distance away, maybe 3 miles, and drive another post, and have the heights of the posts at the same altitude, the top of the post at the same altitude. And if you were to put a third post in the middle between the two, then, or even build a wall perpendicularly between the two, then that wall, if the top of it was at the same altitude as the other 2 points, it would rise between the two. And when I say rise, I just mean it would provide a wall that is higher than the line connecting those 2 points. So if you don't have a very sensitive altimeter, and I don't know that they make altimeters that sensitive anyway, but you can use a hose filled with water. And there are maple syrup extracting hoses that you can find online, maybe 5/16 inch inside diameter or 3/8 inch inside diameter. And if you fill those hoses with water and hold up the 2 ends next to each other, you'll see that the water levels always balance out where they're at the same. Now, that's because of pressure of the air above them is the same. If you were to suck on one of the tubes, the water would rise in that tube and go down in the other. And if you were to blow on one of the tubes or subject it to increased air pressure, then the water would go down and the water balanced on the other end of the tube would rise. So this can be checked when you're holding the 2 ends right next to each other, that the water levels are the same. And if you take the other end far away, it'll still have the same altitude. It'll still have the same level. And you can verify this by going to your backyard or any open space and finding a water level at a certain height, or marking a certain height at one location. Say on your back door, mark a height with a pencil mark, and then use your hose at that location, one end, and the other end of the hose at another location, maybe a tree along the fence line somewhere in the backyard, and mark a place on the tree that's at the same altitude as the place on the door frame. And you can do this several times, like go to 10 different trees around the backyard, always marking at a certain height, and then propagate that level to each tree, from one tree to the next tree, or to the next object, whatever's out in your backyard that you're marking on. If you had a shed, for example, or a basketball pole or something like that. And then when you get to your last tree or post or whatever, and you mark it, then you can check that mark, that height, to the original mark on the back door, or whatever you originally marked. And if they match up, then you've become familiar with the ability of this hose with the water to propagate a level. Now, if it's off a little bit, then you're able to determine how accurate your system is and what kind of losses of accuracy can be expected. Now, sometimes you may err a little high on one tree or a little low on the next. On average, they'll balance out, unless for some reason you have a tendency to always mark high or always mark low. But you might be able to do several experiments and correct for that. So when you find this stretch of flat land, relatively flat land, perhaps somewhere in Kansas or Florida, somewhere that's known for flatness. And when I say it's known for flatness, I don't mean actual flatness. I just mean smoothness of the sphere of the Earth. So it will be expected to still have that curvature, just no mountains or hills and no valleys. Anyway, so the experiment is that you drive one post, and it has a top, and then you propagate a water level to a distance halfway to wherever you're going, and you put a post there and build a wall there, and then continue traveling on further another distance, propagating the water line however long your length of hose is. Maybe 500 feet is a fairly manageable length of hose for a 5/16 inch inside diameter hose. And when you get to the end, drive another post and have its top right there at the water level, so that the height of the first post, the height of the wall, and the height of the end post are all the same height, all the same altitude, and all at the same water level or air pressure level. Now, you would not want to use a telescope with this experiment to see from one post to the other post, because a telescope has a large or a wide lens, or a large lens at one end where all the light comes in, and that leads to blurriness or diffraction. So what you can do to get past that is to shine a light off in the distance, and light tends to travel in a straight line unless it's going through mediums of different density, or like traveling through air that's denser and lighter. This can create a mirage if you are traveling through different densities of air because of refraction. But you can see a light far off in the distance. Like, for example, you might be outside of town 10 miles, and you can see the lights on a skyscraper 10 miles away. Well, it's supposed that the light is coming to your eye in essentially a straight line. So you can use that fact and put a light on top of your end post, your far away end post, and shine it towards the front post. And that middle wall, if it intervenes and comes between the two, then that supports that the earth is curved. However, if the light shines above the wall directly to your eye, which is situated at the top of the front post, then the light is passing over the wall, and all are at the same altitude, and everything is flat. So that would be a good experiment. Now, that 8 inches per mile squared formula is good for I believe several hundred miles. It's a fairly accurate approximation for good distance. Now, another experiment that can be done is to take a weather balloon up into the air with a camera and a level. There's a distinct difference between below the horizon and above the horizon, where there's earth versus where there's sky. And as you ascend in a balloon, the edge of the horizon should go lower to your eye level. And you'd have to do some calculations to see what the drop is, and maybe there are computer modeling CAD programs, you could set the radius of a circle at 3939 miles, 3,939 miles, to approximate the radius of the Earth. And then use that CAD software to find out what the angle of to what extent the angle declines or is lower from a tangent to the Earth's radius. Or basically what angle below level you can expect the horizon to be. And then when you send a balloon up with some apparatus or contraption that has a camera, the camera can see the horizon, and it can also see the level marker that should stay level. And the horizon on a sphere would at some point be noticeably lower than level. However, if the Earth is flat, the horizon will always be at the level, essentially. Now, another experiment is this. I'm not exactly sure how the physics of the Earth work with the magnetic field of the Earth, or electromagnetic, if there's an electromagnetic field, and it changes at different locations. But a gyroscope, when spinning, always tends to hold its axis of spin. And there are fast airplanes these days that can get from one point on the Earth to another point on the Earth. And if you were able to take a gyroscope, set it spinning, and set its axis of spin away from the Earth, then when you travel to any different point on the Earth's surface, that vertical axis of spin should no longer be vertical to the Earth. Now, I believe airplanes do have gyroscopes in them to determine level, so that the airplane knows when it's flying up and ascending, or when it's angled down and flying down and descending. And to my understanding, it is my guess that those gyroscopes in airplanes are on a gimbal with 2 or 3 degrees of freedom, such that the axis of rotation of the gyroscope is free to maintain its position in space. And I don't know that airplanes have anything more than just a gyroscope, and that gyroscope always maintains a level axis, or a steady axis in relation to the Earth. And it may be because of that airplanes that do travel over curvature of the Earth, and yet the gyroscope stays the same, that indicates that the Earth is not curved. if that's indeed what the gyroscope in an airplane is like. But if you could build a gyroscope on a double gimbal or something, which is kind of like if you've ever seen those spill-proof bowls. That's a bowl within a sphere, within some kind of shell. The bowl always is able to stay level because of the axis of rotation that the concentric spheres are hooked onto one another with. And an object attached to an axis of rotation, that axis of rotation and that attachment is called a gimbal. And they make gimbals for cameras so that you can have a smooth camera shot even if the cameraman is moving and shifting his position and rotating the camera contraption surrounding the camera. The camera will maintain its momentum and always be pointing in one direction. So that's what a gimbal is. And gyroscopes on gimbals in airplanes, if they're always maintaining a constant angle with respect to the Earth, perhaps like something normal or directly out from the center of the Earth, something vertical. And if that's used to determine level for an airplane's instruments, then that indicates that the Earth is flat. Unless there's some kind of compensation, maybe mathematical or a computer program that compensates for the gyroscope in the airplane based on how far you've traveled and in what direction. But I doubt it, and so that kind of supports the flat Earth there. If you can take a gyroscope on a gimbal in an airplane and travel a distance over the Earth, and it maintain its same vertical standing, for example, same axis of rotation, then that would indicate that the Earth is flat. Unless there's something weird about the electromagnetic field of the Earth is directly related to centripetal force or centrifugal force of the gyroscope, and thus changes it as it travels. Now, I don't think you'd expect to find that on a globe. No, I think with a globe, you would expect the gyroscope to keep its axis in relation to space, in relation to the stars, and as you fly your plane, your sense of level changes from the gyroscope, which maintains its sense of level. So that'd be an interesting experiment that could probably be fairly affordable. Now, the next experiment is to go to a far south country, and there are three such places: Australia, South America, and South Africa. But South America, the southern tip of South America, is the most southern. Now, all the continents are mapped. Their outside surface, or their outside edges, are mapped based on ocean traveling and instruments using the stars to locate coordinates of latitude and longitude. And so a ship would sail around a continent, like, for example, sail around Australia, and at every point on the shore, a measurement would be regularly taken against the stars to determine, and considering the time of day, a measurement would be taken to determine the latitude and longitude at that point on the shore. And the ship would travel around the whole continent or whole island or whole region of land around its shore and take measurements everywhere and build up a list of coordinate points. And then that could be translated or transferred to a map. Now, if you translate it onto a sphere, you would get the coordinates in the map such as we have on the globe. And if you translated it to a flat Earth map, so an azimuthal equidistant projection, having the North Pole as the center and the South Pole as a circumference at the bottom latitude, then you would have the flat Earth map with the stretched out continents in the southern hemisphere. And assuming that there's no change in the way distances behave in the southern hemisphere and at different latitudes, then we would expect the coordinates for the distance far out there, like in South America, between any two cities, for example, on an east and west direction, we would expect that distance to be a stretched out distance. And in France, the explorers used metal chains that did not stretch so much. They used metal chains in order to stretch distances, to measure exact distances between 2 points, like between, for example, the peaks of two mountains. And thus in the mapping of Europe with early explorers in the 1800s. Explorers and map makers. So what this final experiment, there's one more after this. What this experiment would involve is taking some lengths of chain, long lengths of chain down to South America, very low in latitude, and measuring an east-west distance, like perhaps between the Pacific and the Atlantic shores, or between any two cities that lie on an east-west distance, and then measure that distance with the chains and see if it's like 1.8 times what the globe predicts it would be. Now, one thing I did not think about with the going up in an airplane and the gyroscope is that you could actually build a gyroscope here on the surface of the Earth, and in however the Earth rotates in space, that gyroscope will keep its axis in relation to space, which is pretty much stable as far as the stars go in the current in the currently accepted cosmological model. And so if you were to set a gyroscope up and have its axis pointing at any star, then it will maintain that position pointing at that star. And we talked about star trails in the first video, So if I was to set a gyroscope up and point its axis at the North Pole star, it would pretty much stay pointing there all the time, because the North Pole star does not does not change its place in the night sky. Whereas if you swing an angle away from the North Pole star to any other star, it circumscribes a circle around the North Pole star. And the fastest moving circle, the largest circles are in the ecliptic plane area, which is like above the equator. And so that's where you see the constellations of the zodiac, and also the path where the sun and the moon and the planets are. And that's where all the eclipses happen. And that may be why it's called the ecliptic plane. So if I was to set up a gyroscope and say point it at Orion, then as the night progresses through the night, then Orion will be seen beginning in the east, just like where the sun is, and going along a circular, the path of a circle across the sky through the night, and it will go from one place coming up over the earth to above us, or not directly above us, but on its circle, and then continue on down, sink below the horizon in the west. And if I was to point a gyroscope at those stars in space, that gyroscope would maintain pointing at Orion, and I would see the gyroscope I would see it following the star. Come to think of it, this is a interesting experiment. This would be a good invention. You could have a telescope, and if you wanted to study a star or a planet or the moon or anything, have a big apparatus with a gyroscope and a telescope attached to the same axis, or attached to the axis of the gyroscope in some way, so that since the gyroscope is fixed in space, then so will the telescope, and you don't have to worry about a mechanical gearing that moves your telescope to track a star. The telescope will be self-tracking of the stars in space, and you might have a lot of stability with a system like that. Now, if you put the gyroscope pointing at a star and you track it, then you should see your gyroscope moving in relation to the surface of the Earth. So over a day, it will make a full circle. And I didn't think about, when you get on a plane, if you're flying against the rotation of the Earth, then in that case, the gyroscope would stay the same. If you were to fly against the rotation of the Earth at the same speed as the rotation of the Earth, then your gyroscope would appear to stay pointing upwards. Whereas if you were to fly in the same direction as the Earth, but at that same speed, then as you travel along the surface of the Earth, the gyroscope would be appear to be moving in a circle twice as fast. Now, the next flat Earth experiment uses a sniper rifle, a high-powered sniper rifle that's able to shoot maybe a mile or two or more. And you want to take advantage of the Coriolis effect in this case. What you're doing is determining whether the Earth is spinning, a spinning globe, and the best place to do your Coriolis effect sniper rifle experiment is north of the equator, somewhere in the closer to the pole, like, and it's either north or south, just away from the equator. You have the greatest Coriolis effect the farther you are closer to the poles. So maybe if you're in the United States, in one of the northern states. But if you shoot a bullet to the north, you're traveling faster than your target because you have a larger circle of your latitude than your target does, because it's further north. It has a smaller circle. and so it's not traveling as fast. And if you shoot a bullet at a target, first you would want to calibrate your weapon by shooting east and west where there is no Coriolis effect, and make sure that the bullet light falls somewhere on the vertical axis of where you shoot. And then when you aim your gun north and fire, if the bullet fires to the right of where you're aiming, then you know how much it should fall to the right according to the Coriolis effect, by seeing what your latitude is and the latitude of your target and how long it takes the bullet to arrive at its target, how much your position would have moved relative to your target's position. You can also fire to the south, and in that case the bullet will still curve to the right, because if you're firing to the south, then you're firing to something that's moving faster because it has a larger circle of latitude. You can also, with a sniper rifle, do an east-west experiment, and the difference here is that the greatest effect will happen when you're at the equator, and it's a matter of firing east or west and the bullet falling too high when you're firing east, and falling low of the target when you're firing west. And you would want to calibrate your sniper rifle to shoot at a particular height according to the scope, by shooting north and south where there is no effect from the Earth spinning and rotating away from the line of fire. I had another thought about putting a camera, hanging a camera from a weather balloon and sending it up several miles. That if your camera is attached to something that's hanging vertically, then the camera, as long as there's no wind or shaking or swaying of whatever the camera is attached to, it's attached to what's known as a plumb, something that always is heavy and hangs downward, and the camera will be vertical and maintain its verticalness as long as it's not swaying or rocking from wind or being jostled. And as you wouldn't need a level, actually, just the camera pointing out to the horizon, and then as the balloon ascends and you're recording with the camera, your later pictures, when the camera's up way high, will be taking a different picture than your low pictures when your camera's down low. And you can compare the early pictures and the later pictures to see if the horizon line has gone down for the later pictures.